begin Unit 1 in Chapter 2. There is some important material about measurement in Chapter 1, but that is going to be covered in the lab, the first lab. So Chapter 2 is about straight line motion or linear motion. Things that are moving horizontally in a straight line, or perhaps something that's falling straight down in a straight line. And before we can describe that motion or any motion, we're going to need a frame of reference. If we think about a bus that's traveling, let's say we have a long straight highway and we have a bus traveling 50 miles an hour to the east. A passenger at the back of the bus gets up and walks towards the driver, and he's walking at a pace of 5 miles per hour. You probably didn't even think about it, but you're assuming that I mean 5 miles an hour relative to the bus. If there wasn't somebody standing outside by the highway and could see into the bus, if the bus is going 50 miles per hour to the east and a person gets up and walks 5 miles per hour relative to the bus, to the front of the bus, it will look like that person is going 55 miles per hour relative to the earth. Most of the time in this class, we're going to be taking the frame of reference of the earth. We'll be looking at things relative to the earth. Now, truthfully, we all know the earth is actually not stationary, but it feels stationary to us, and it makes a good frame of reference. We need a way of defining directions and things, and so we use a coordinate axis. Fortunately, a coordinate axis in physics looks exactly like a coordinate axis in mathematics. If we think in terms of x and y, we usually treat horizontal motion as being x, vertical motion as being y. We also, though, at times in physics, will use what I call compass directions, in which case this would be east, this would be north, the negative x-axis would be west, and the negative y-axis would be south. So we might talk about something with a position or velocity that's north or east or south, as opposed to just always using x's and y's. To describe something's position, position is just where its location is in your frame of reference. Let's assume we're going to just be talking about horizontal motion right now. We would represent that with x. That would be the location. It's important to understand that position is a vector quantity. We haven't used the word vector before. What makes it a vector? Well, there's two types of measurements we deal with in physics. One is vectors, one is scalars. The difference is vectors have a direction. Things like time and energy don't have directions, but things like position and velocity and acceleration and forces do. So position is one of the things that has a direction. It has an SI unit. That's our standard unit of the meter. So normally when we measure position, it could be 2 meters to the left or 17 meters to the right. Now, meters is not the only unit we can use. It can be any unit of length, but the SI unit happens to be the meter. Vectors. Have magnitude which is just a science word that means size, and direction. Anything that is a vector is going to have a size as well as a direction. We can talk about somebody's position as being 5 meters east, 13 meters south. A lot of times when we do that, we will actually use positive and negative signs. In this case, his position would be positive 5 meters. And in this case, his position, notice I said south, so that's actually on the y-axis. His position would be negative 13 meters. So we can use positive and negative signs to indicate direction, as well as using words like north, south, east, west, left, right. Displacement, that's the next term we're going to look at. And our symbol for displacement is going to look like this. That is the Greek letter delta. It means a changing. You saw that in Algebra 1 when you were doing change in x over change in y. I said that backwards. Change in y over change in x. And it represents a change in position. It is a vector, so the change in position also has a direction. He moved 15 meters to the north. He moved 3 meters left. You have to keep in mind that it is a vector. It does have an SI unit. That is also the meter. It makes sense that if we measure position in meters, we would also measure change in position in meters. So a simple example. Joe walked 15 meters east, then 9 meters west. What was his displacement? Vectors can be drawn as arrows. It's really helpful to visualize. So let's suppose that he's starting right here. There's his beginning point. Joe walked 15 meters east, and then he turned around and he walked 9 meters to the west. That was east, this was west. Displacement is his change in position. Where is he now compared to where he started with? Well, obviously, if he goes 15 meters this way and 9 meters this way, he's 6 meters from where he started. He went a positive 15 meters, and then he went a negative 9 meters. He ended up 6 meters east. Notice displacement, although it's similar to distance, is not the same thing. His distance, which would be scalar, the distance walked would be 15 meters plus 9 meters is 24 meters. Distance is scalar. Scalar quantities do not have a direction, so there's no such thing as a negative distance. All distances are positive. So when he walks 15 meters and 9 plus another 9 meters, if somebody said, what distance did he walk? He walked 24 meters. But when they ask about displacement, they're saying, where is he now compared to where he started? Well, he started at 0. He ended up at 6 meters east. Another formula you'll often see for displacement is that the displacement is your final minus your initial position. Some people will use x2 minus x1. In this case, his final position was 6 meters. His beginning position was 0. We let him start at a place we considered the origin. So his displacement is 6 meters. All right. I hope everybody understands the difference between position, that's your location, displacement, that's your change in position. Where are you now compared to where you started? Did you move 12 meters one direction or 15 meters another direction? And finally, distance. And distance is exactly what you think it is. It's just the sum. How far did something move? Now the section 2.2 in the book deals with velocity. Many people think speed and velocity are the same thing, but they're not exactly the same thing. Even though in everyday language we often think of them as the same thing. Your average speed is the distance traveled divided by a time interval. Speed is scalar. It's easy to remember they both start with S. So, if I know that Mary drove 150 miles in 3 hours, then I can find her average speed by saying 150 miles over 3 hours is 50 miles per hour. Now notice when I find her average speed, it does not tell me anything about instantaneous speed. Part of that time she might have been going 70 miles per hour. Part of that time she might have been 35 miles per hour. Part of that trip she may have been parked at Sonic getting a large Diet Coke. So average speed tells us just that. It doesn't give us what we think of as being an instantaneous speed, which is what's happening right at that second. If you're in your car and you look at your speedometer, it will tell you an instantaneous speed. But an average speed is just the distance divided by the time, and it gives you that average. Velocity, which is symbol for velocity is a V, is a vector. We now know that means that velocity has to have a direction. Some people, especially when you're talking about straight line motion, will say that velocity is speed with direction. It has an SI unit, the same SI unit as speed, which we measure distances and positions in meters, time in seconds. And average velocity is displacement divided by time, or change in position divided by, I should put time interval, how long did this take, change in time. That line over the V is just a mathematical symbol. It means average. Another way you might see this written is that's the first position, that's the second position. So a change in position is the second position minus the first position, and we're T2 minus T1. Either one of those. So let's look at an example. A runner started at the 50.0 meter mark. 3.0 seconds later, she was at the 30.5 meter mark. Let's find her average velocity. Her average velocity, change in position, change in time. Well, her final position was the 30.5. This is x2. Her beginning one was at 50. And they tell us that the time interval was 3.0 seconds. That's going to be a negative 19.5 meters divided by 3 seconds. Means my average velocity is negative 6.5 meters per second. So obviously she was running in the negative direction, but that's easy. If you picture a number line, here's the 0 meter mark, here's the 50 meter mark. If she started off here running, and later she was here, she had to run in the negative direction. She had a negative displacement. A negative displacement means you're going to have a negative velocity. There is a second part to this question. I'm going to have to erase since this is a little bit crowded. I'm going to write my answer down. If she maintains a pace of negative 6.5 meters per second, how far will she travel in 10 seconds? where will she be? Well, the only formula we've really looked at so far is average velocity, so we'll go there. Average velocity is change in position, change in time. If I rearrange that, I can see that her displacement or her change in position is just her average velocity times the time. If you remember middle school, you might have had a formula that looked something like distance equals rate times time. How far you travel is your velocity times your time. So here we have negative 6.5 for 10 seconds. She's going to travel or have a displacement of negative 65 meters. If we just want the question how far she travels, you could say she traveled 65 meters. The negative tells us she's moving in the negative direction. The second part says, where will she be? Well, we know that displacement is your final position minus your initial position, your change, or we rearrange this, it's going to be where did you start plus how much did you add to it. Well, in this case, she started at the 50-meter mark. She ran, her displacement was negative 65 meters. So her new position is that she's going to actually be at the negative 15-meter mark. Again, if you look at a number line, that's going to make excellent sense. She started at the 50-meter mark, and she ran this direction for 65 meters. That's going to put her, this is the origin, at the negative 15-meter mark. So that's just a simple example using the idea of average velocity, and just to make sure you understand how distance and displacement are different than speed and velocity. All right, we've been talking about average velocity, but there are times when we would like to talk about an instantaneous velocity. I've already hinted that if we're in a car, we know the speedometer will give us instantaneous velocity. Instantaneous velocity could be considered average velocity, but over a really, really short time interval. Not over 3 hours, maybe over a second, maybe over a half of a second, maybe over a tenth of a second. So basically, the formula for the velocity, notice I don't have an average bar this time, it's the limit. As our time interval goes to 0, change in position over change in time. If you've already taken calculus, then you understand that this limit as this time goes to 0 is actually a derivative. It's dv dt. So the instantaneous velocity, dx dt, the instantaneous velocity is the derivative of the position. It tells you how the position is changing. If we look at a position time graph, and we put time, I'm going to draw a graph, looks something like this. This is our position, and this is time. Call it x1. And you can see that would be t1. We might have a later position, x2. That'd be t2. Make a little more room. We could come way up here where it's pretty flat. So draw it perfectly flat. That's a different time. And even a fourth time. So P1, P2, P3, P4. We can look at position as a function of time. The derivative is essentially the slope. So we can tell just by looking at our graph that at P1, the slope is positive, so we can tell that the velocity is positive. Same thing for P2. Velocity is positive. If we look at the third position, it looks like the slope is 0. That makes sense. We hear the position is increasing, more and more positive, you're getting farther away. Here the position is decreasing, but for just a minute, the velocity had to be 0. And then finally, at P4, we can see the velocity is less than 0. We're moving in the negative direction here. Moving in the positive direction, getting farther and farther away from the origin. This would be the point at which we actually turn around, and now we're moving in the negative direction back towards the origin. Positive velocity, positive slope, 0 velocity, 0 slope, negative velocity, negative slope. Now, we can also get the average velocity between 2 points by simply getting the slope. If I want the average velocity from P1 to P2, I need the slope of this straight line that connects them. Notice it may not exactly match that curve, but the average velocity from point 1 to point 2 would just be change in position, change in time. So position time graphs give us a lot of information about velocity. We can look at it. If we pick 2 points, I can get the average velocity from here to here. I'd get a very different answer. What if I wanted the average velocity from point 2 to point 4? That would be the slope of that line. Notice that would be an average negative velocity. I don't have any numbers, I can't calculate it, but I could do an average velocity from P2 to P4. And that average velocity would be x4 minus x2, t4 minus t2. But I can look and tell that would be negative. This looks exactly, if you change an x over change in t, like slope you learned back in Algebra 1. Okay, let's do a little bit more with this idea of instantaneous velocity, and that the instantaneous velocity is a derivative. Suppose a jet's position is given by the function x of t equals at squared plus b. And then over to the side, they tell me a is equal to 2.10 meters per second squared, and b is equal to 2.80 meters. So I can get this with the numbers in. So my position function is 2.10 t squared plus 2.80. It's going to be in meters. First question says, find the displacement from t1 equals 3 seconds to t2, which equals 5 seconds. Well, I know that displacement is just going to be change in position. So x of 5 minus x at 3. I just plug in the times. I'm going to have to calculate those out. X at 5 is 2.105 squared plus 2.80. Comes out to be 55.3 meters. The position at 3 seconds was 21.7 meters. All I have to do is then subtract x of 5 minus x of 3. When I do that, I have 55.3 minus 21.7 is 33.6 meters. So the answer to the first question is that from 3 to 5 seconds, the displacement was 33.6 meters. The second question says, what was the average velocity during that time period? So let me just write down here real quickly that. I'm going to erase that. There's the results of our first question, part A. From 3 to 5 seconds, our displacement's 33.6 meters. Our second question here in this example says, what's the average velocity during that same time period? Well, the average velocity is simply the displacement over the time interval. In this case, we've already found the displacement was 33.6 meters. From 3 seconds to 5 seconds, that's a time interval of 2 seconds. So our average velocity is 16.8 meters per second. I'm going to write that right here. Average velocity, 16.8 meters per second. Displacement divided by the time interval. Third part of the question says, find the instantaneous velocity at t1 equals 3 seconds and t2 equals 5 seconds. So we find two different instantaneous velocities. Instantaneous velocity is given as a function, as it's the derivative of the position. I need to find that function. v of t is x prime of t. Well, what is the derivative? If I take the derivative of the first term, I get 2 times 2.10 t. The derivative of 2.80 is simply 0. So the velocity function is simply 4.20 t. If I plug in 3 seconds, I get 4.20 times 3 comes out to 12.6 meters per second. That's the velocity at 3 seconds. If I plug in 5 seconds, 4.20 times 5, it comes out to exactly 21.0 meters per second. Notice that seems reasonable. Our average velocity was 16.8 meters per second. At T1, our velocity was 12.6 meters per second, but at T2, it was 21.0. So knowing the average velocity does not tell you what's going on at any particular time. We could actually plug in and find out what was going on at 4 seconds. If I did 4.20 times 4, I'd get, coincidentally, 16.8 meters. All right. That concludes average velocity, average speed, instantaneous velocity. We're going to move on to acceleration. This is section 2.4 in your book. What you need to know is that acceleration is any change in velocity. Speed or direction. What that means is there's exactly 3 ways that you can have an acceleration. You can speed up, you can slow down, or you can change your direction. All of those things, speeding up, slowing down, changing direction, change your velocity. And any change in velocity is an acceleration. Now, acceleration is a vector. The direction of acceleration is going to be important, and our standard SI unit is going to be a meter per second, or a meter per second squared. Average acceleration is simply the change in velocity over the time interval. So our average acceleration, and again I put the line over the A to indicate average or mean, is a change in velocity over a change in time. If you want, this could be written out also as final, or V2 minus V1, T2 minus T1. Looks very much the way the relationship between acceleration and velocity looks just exactly like the relationship between velocity and position. Let's do an example of an average acceleration problem. accelerates from rest. Notice when it starts from rest, that's another way of saying the beginning velocity is 0. It was in part. To 90 kilometers per hour in 5 seconds. Find the average velocity, the average acceleration in meters per second squared. Okay, we're going to have to deal with units in this problem. They've given me the velocity in kilometers per hour. They've given me the time for the acceleration in seconds, and they want the answer in meters per second squared. It is possible to talk about acceleration that's not in meters per second squared. I'll do that first. Average acceleration is simply change in velocity over change in time. In this case, our velocity went from 0 to 90 kilometers per hour. So our change would be 90 kilometers per hour minus 0. Our time interval was 5 seconds. So we could say that the average acceleration was 18 kilometers per hour per second. What does this mean? It means that each second, the velocity is changing by 18 kilometers per hour. It's changing 18 kilometers per hour every second. So it started from 0, it was going 18 kilometers per hour, then 36 kilometers per hour, then 54, then 72, then 90. Each time just going up 18 kilometers per hour. But that's not the units they asked me to use. They asked me to get it in meters per second squared. I need this 90 kilometers per hour in meters per second. That's really pretty easy to do. I have 90 kilometers in 1 hour. I know 90 kilometers is 90,000 meters. I know 1 hour is 3,600 seconds. 90 kilometers is 90,000 meters. 1 hour is 3,600 seconds. So it's going 90,000 meters in 3,600 seconds. That comes out to be 25 meters per second. If I use that instead of 90 kilometers per hour, I get an average change in velocity over change in time, 25 meters per second. Still started from rest, over 5 seconds. And I get 5.0 meters per second, which we write as 5.0 meters per second squared. This is an actual measurement of acceleration. 18 kilometers per hour per second is great. It's just not the units we were asked to provide. It's more traditional to stick to meters and seconds. So by changing this 90 kilometers per hour to 25 meters per second, we can see that our average acceleration is 5 meters per second squared. Again, that's just an average over that 5 second period. We don't know for sure anything that's going on in the middle there. You may hear people talk about deceleration. When people use the term deceleration, they mean slowing down, a change in speed. We don't usually use that term in physics, and acceleration can be an increase or a decrease in speed. It also can just simply be a constant speed but changing direction. So if you change direction, you're accelerating. If you're getting faster or slower, you're accelerating. But when lay people use the term deceleration, they usually mean you're slowing down. It's also important to realize you can have any combination of a positive and negative position, a positive or negative velocity, and a positive and negative acceleration. If you, let's say you have some arbitrary origin on a highway, long straight highway, we'll keep it linear, and you're currently at the 300-mile marker, but you're traveling to the west, and the mile marker is going positive is to the east. So you have a positive position because you're at the 300-mile marker, but you're traveling in the negative direction. You're heading back towards the origin. So you have a positive position, you have a negative velocity. If you slow down while you're traveling back to the origin, you'll actually have a positive acceleration. Anytime that velocity and acceleration are in the same direction, and a lot of times with that means they're going to have the same sign. They're either both positive or both negative, but if they're in the same direction, speed increases. So if you're driving down a highway going north and you step on the gas pedal, your acceleration is also to the north and you're going to speed up. When velocity and acceleration are in opposite directions, where they have opposite signs, speed decreases. So if you're driving to the north and you step on the brake, your acceleration is to the south. Your velocity is to the north, but your acceleration is to the south, and you're going to slow down and stop. Anytime something's gaining speed, getting faster, you know velocity and acceleration point in the same direction. Anytime something's slowing down, you know velocity and acceleration are pointing in opposite directions. Okay, we've only talked about average acceleration, so we need to talk about instantaneous acceleration. In instantaneous acceleration, the acceleration is equal to the limit as the time interval approaches zero of the change in velocity over the change in time. Or instantaneous acceleration is the derivative of the velocity. When we look at velocity time graphs, and we'll just make it look something like this. That's the first velocity. That's the first time. Here's a later velocity. Here's a later time. The slope of the velocity time graph gives me the acceleration. If I use 2 points that are spaced far apart and I find the slope between those 2 points, that's going to give me the average acceleration. On the other hand, if I find the slope at a particular point, that's going to give me the instantaneous acceleration. Let's do an example with instantaneous acceleration. suppose we have a position function x of t, 2.10t squared plus 2.80. Coincidentally, we've already looked at this particular position function, and we wanted to find the average acceleration from 3 to 5 seconds. Well, average acceleration in this case is just the change in velocity over the change in time, or the velocity at 5 seconds minus the velocity at 3 seconds over the time. We figured this out a little bit earlier in this video. We found that at 5 seconds, this function gave us a speed of 21.0. At 3 seconds, it gave us a speed of 12.6 meters per second divided by 2 seconds. And my average acceleration is 4.20 meters per second squared. These figures here came from the earlier example where we calculated the instantaneous velocity at 5 seconds and it was 21 meters per second. The instantaneous velocity at 3 seconds was 12.6. So we got average. What about instantaneous? Instantaneous acceleration is going to mean we need to do a little bit of calculus, a little bit of derivatives. So we'll do that. I'm going to write this answer right here just because we may want to look at that in a minute. The average was 4.20 meters per second squared. The velocity function is just the derivative. So that was 4.20t. And the acceleration is the derivative of the velocity, which would be 4.20. Notice this is not actually a function of t, so we had a constant acceleration of 4.20 meters per second squared, as well as an average of 4.20 meters per second squared. All right, I'm about to finish this section, this video, but I just kind of want to remind you, if you want to go from acceleration to velocity, I said that one. If you want to go from position to velocity to acceleration, you take a derivative. You do dx dt, that's going to give you your velocity. You do dv dt, that's going to give you your acceleration. All right, now that we've found one that has a constant acceleration, in my next video I'm going to do lots of examples of solving problems that involve constant acceleration.